Hi everyone, I am Manas Pratim Das. We would like to share with you our work on online photometric calibration of automatic gain thermal infrared cameras. In the recent years, we have seen that the thermal cameras have become better, smaller, and are commercially available at lower costs. They are therefore being used in a wide range of applications, and in robotics, we see them being used in self-driving cars and autonomous aerial vehicles, etc. They have become an interesting source of information for subterranean exploration, like we saw in the DARPA challenge. The trend is only growing. Therefore, we would like you to think about this question. Do we require special algorithms for the thermal infrared domain? We have seen tremendous development of computer vision algorithms over the past decade. Most commonly than not, these algorithms are developed primarily keeping in mind RGB cameras. Hence, a natural question is that can we use these algorithms for thermal infrared cameras as well? The answer to this is mostly no. And one major factor is due to the violation of photometric assumption. We will discuss more on this later. Therefore, there has been work on porting algorithms to the thermal infrared domain. However, if you can bridge the gap between the thermal infrared and RGB domains, we can potentially remove the need to port each and every algorithm. So this is our contribution. In this work, we present a calibration algorithm which assists the downstream application satisfy the photometric assumption. Now, what is the photometric assumption? The assumption states that the appearance of an object should remain the same regardless of which frame you view it from, or regardless of which location in the image you view it from. In the first example, we see that the appearance across time is not consistent. We term this as temporal variation. In the second example, the appearance varies as it is being viewed from some other location in the image. We call it spatial variation. Here is a sample of the dataset we use to provide you a feel for these inconsistencies. Notice the drastic and quite frequent changes in the photometric appearance. In the next clip, we show the performance of a popular visual odometry software, which is state-of-the-art in the RGB domain, but here we see it lose track and require reinitialization. Source of these photometric errors is tightly tied with the sensor data acquisition. A thermal camera has many of these microbolometers, each of which contributes to a pixel in the image. To maintain high contrast in the image, the camera adapts the grayscale range based on the scene. However, as the scene changes, we can expect the camera to introduce temporal variations. Since these cameras are uncooled, the individual sensors get heated up non-uniformly to build up residual heat during their operation, which results in spatial variations. The characteristics of these variations are very different as compared to the RGB cameras. Finally, our objective is to develop an online algorithm that sits in between raw data and other downstream applications and to correct for these variations. Additionally, we require the algorithm to perform at least more than 60 FPS, that is frame rates per second, and it should work for any thermal camera without requiring manual calibration. The closest related work is photometric calibration algorithm developed for RGB cameras. However, as we will see in the results, it usually makes the calibration worse. Without automatic calibration, the cameras will require manual calibration or knowledge of the scene in which they are operating. Such requirements make the applicability limited. We will go over our contributions now, but first we keep the requirements list handy to tally the progress. Our first contribution is the image acquisition model, which is specifically developed for the thermal infrared domain. This model relates two corresponding pixels and reasons about the temporal and spatial variations between them. Our model can be applied to all thermal infrared cameras, thus fulfilling the generalizability requirement. We perform the calibration after observing correspondences across multiple frames without requiring any manual calibration. However, there is a chicken and egg problem. Photometric errors leads to bad pixel correspondences, which can adversely affect the calibration. We employ an outlier rejection scheme and decompose the problem to achieve real-time throughput. Multiple correspondences, as we saw in the image above, also helps us deal with noisy correspondences. Online data means that we do not know the range of temperatures we would observe during the run, and this requires special adaptations utilizing the domain knowledge of the thermal infrared cameras. This adaptation also helps us preserve the image contrast. Going back to our previous diagram, we want to evaluate the impact of our work across a wide variety of CV applications. We therefore evaluate against both low-level and high-level vision algorithms. Low-level vision tasks such as feature tracking can also be categorized into three major groups, namely direct, semi-direct, and indirect. We use only the first two, the direct methods and the semi-direct methods, as they rely heavily on the photometric assumption. As cited earlier, the closest related work is an algorithm developed for RGB camera, which we also use as our baseline. Here is a qualitative result showing frames over time. The bottom row shows that after calibration, the images look very consistent. Qualitative result when running high-level algorithm, namely the visual odometry on calibrated dataset, shows that our method prevents loss of feature tracking, which is very critical and also maintains good image contrast. The baseline developed for RGB cameras was unable to maintain the already low contrast available in the thermal images, due to which, even if it lost the features, it was unable to reinitialize. Overall, from the quantitative results, we observe significant performance improvement. An interesting observation is that the baseline calibration resulted in worse performance than the raw dataset. We will talk about the possible reasons later. I will wait in the slide for a moment for you to read the interesting parts. Our implementation runs only on CPU and can benefit from multi-threading. Running on a single core, we observe that our method meets the real-time requirement. The temporal parameters which are needed to be estimated every frame requires only 0.01 seconds, giving the method an throughput of 100 fps. The special parameters are required to be estimated only once per dataset or only once per run. Estimating those parameters requires only 0.027 seconds. To conclude, in this work, we provide evidence that not all algorithms can be ported directly from the RGB domain to the thermal infrared domain. Secondly, we observe that RGB photometric calibration resulted in worse performance. We think the two reasons for this might be, number one, the RGB photometric model is not compatible with thermal infrared cameras. While the RGB photometric model uses radial vignetting as the spatial variations, In the thermal infrared domains, the spatial variations do not follow symmetrical model and can be non-uniform. Photometric errors in the thermal infrared cameras are more extreme and frequent. The RGB calibration algorithm was requiring frequent resets because of this, which then ended up introducing additional photometric errors. So the RGB algorithm was not developed to handle the extreme and frequent photometric errors that appears in thermal infrared cameras. It was also not able to preserve the contrast of these images, and as you saw in the qualitative results, the contrast of the thermal images already were very low. For the source code and more information, visit the following link. Now I will let the qualitative results run and would be happy to answer any questions. Thank you for listening.